Right, the second presentation is titled Integration of Western Systems and Weapons on Russian Fighter Aircraft. And we have a team of 2 Indian Air Force test pilots, Wing Commander M.K. Shakir and Wing Commander A. Sinha. Basically, as we are all aware, the Indian Air Force has got both Russian as well as the Western systems. Integration of Western systems, weapons on fighter aircraft on Russian origin significantly enhances the suitability and employability of these aircraft. That goes without saying, because we've got the both systems, and we would like to capitalize on the positive traits of both of these that we have in our inventory. But of course, there's a downside of it. It is not simple as it appears. Weapon integration involved resolving latency issues, site harmonization, platform-specific air data error, integrating auto-attack features, etc., are challenging. Also, on the other hand, autopilot integration requires extensive rig testing to understand control logic, basically because of lack of visibility into the autopilot control logic, and some of these are still enigma, and people are trying to unravel, especially the Russian systems. So it is a challenging task, but it is not that it has not been achieved. I think there's been a great deal of innovation and a very positive approach on the part of our test pilots, and indeed we see even today a number of those systems adapted across both Russian as well as Western systems. A few words about the 2 speakers. Wing Commander Shakir was commissioned in 1997 in the Indian Air Force. He is an aeronautical engineer, and what is known to us as the AEL, or the electrical stream. He has extensive maintenance experience on a number of Russian background aircraft, Su-30 MKI and the MiG-27. He is, of course, a flight test engineer and presently posted at Aircraft and System Testing Establishment, where he's been involved in a number of projects, including aircraft upgrade programs and the air combat maneuvering instrumentation integration on different platforms, and that is something that is really gathering steam in the Air Force. Wing Commander Sinha, his compatriot, was commissioned in 97, also the same year. He is a qualified flying instructor, which is, in most instances, one of the base qualifications of an experimental test pilot that he went on to become subsequently, and he's with AST now. He's logged over 1,800 hours of flying on various fighter aircraft, including the Jaguar and the Su-30 MKI, and he's presently involved in integration of various avionic systems and weapons on different platforms. So with this kind of background amongst these 2 speakers, I'm sure we are in for a very nice and informative presentation on integration of Western system and weapons on Russian fighter aircraft. So over to the team.
Thank you, sir. And a very good afternoon to you, ladies and gentlemen. It has been covered amply in the previous sessions also that the 2 important aspects of air power that have affected its evolution over the past few decades is its technological dependence and the rapidity of its advancement. These factors have forced the military aviators world over to look into means of modernizing their existing fleet of aircraft so as to maintain them as war-worthy and capable machines. This approach is highly cost-effective, that it not only allows complete life cycle utilization of the platform, but it also reduces the developmental and training costs. As part of the modernization program of the Indian Air Force, we have undertaken many projects involving integration of Russian systems and weapons, Western systems and weapons on Russian platforms. And we would be glad to share our experiences during these projects. During this presentation, we would talk about certain basic challenges. Thereafter, we shall present certain technical issues related to systems integrations and weapons integration. Thereafter, we shall talk about certain aspects of handling qualities and human-machine interface. And thereafter, we would like to answer any questions that you may have. Coming to the challenges. The root cause of most of the challenge is the difference in design philosophy at both macro and micro level. I must emphasize that this difference is not about capabilities or which is superior or inferior system. It is about the method by which a specified capability has been achieved on a particular platform. The bottom line remains that any military equipment under production does what it is supposed to do. To highlight a few of these differences, let us see two aircraft of comparable vintage and role, but from the two worlds. The avionics architecture of even the vintage Western aircraft involved an avionics bus. Therefore, the systems were also designed for bus compatibility. The Russian platforms, on the other hand, were not designed the same way. And it presented a great deal of challenge while integrating the Western systems onto the Russian platforms. Another example, autopilot. Autopilot traditionally has been used extensively on all Russian fighter aircraft, and the use has not been restricted to reducing pilot stress. It has been used for unusual altitude recovery, avoiding ground collision, and for auto mission execution. On the other hand, many Western aircraft of the same vintage did not even have a basic autopilot. The philosophy of weapon employment was also different. You can drop a lesser number of weapons with a greater accuracy, or you can drop a larger number of weapons with not so great accuracy. Either ways, you're going to get your target. But to create synergy between the two philosophies on the same platform can pose very basic but crucial challenges. It is little difficult to visualize the problems that these issues can create, which more often than not, they can be slightly more than keeping awake in this afternoon session. So to keep it a little more interesting, I'll present before you a small conversation between the two worlds. Here we have two ace pilots from the two worlds, one from the west and from the east, and I'll take you about 40 years back, and this is how the conversation goes. A simple question and a simpler answer. It may sound a little funny, but that's true. Another example for the second point that I covered about autopilot. I must remind you that this conversation is 40 years back from now and not of today. Simple, that's all that he does. The question marks and the exclamation can be filled with the procedural recovery or maybe in some cases crash. The third one, this is even more interesting. Perfect answer. And now we'll have another perfect answer. Well, that was on the lighter side, but I'm sure you would appreciate that for these two different people to fly each other's machines would not be easy. However, over a period of time, these differences have reduced, and the modern platforms like the Su-30 are much more receptive to Western systems and weapons. And it is from the point of overall design and their employability. The other challenges that we faced included that many of the legacy Russian fighters did not cater to upgrades by means of isolated integration of systems. Even if they did, that capability was not available with us. The issues ranged from physical space to scheduling of data. One of the major issues was the standards and the specifications that the system conformed to and the platform conformed to were different. Now, this kind of difference would always lead to any kind of interface, whether it be electrical, mechanical, or avionics. The problem was compounded by the limited visibility into the system that we had. However, finding solutions to such issues provided us immense learning as military aviators and a testing agency. Now, having seen the root cause of the technical challenges in these integration, now I would hand you over to Wing Commander Shakir, who would talk about some of the specific technical issues which at times are quite surprising, and I hope that you will enjoy them.
I think it is not ended here. I'll continue to bore you for a little more time. Thank you, Sinha. Integration of a Western system on a Russian platform presents a unique challenge both to the system engineers and to the flight test community alike. In the next few minutes, I shall cover a few of the challenges that we faced as a team and we were able to overcome it with a fairly decent success rate. The first one, perhaps the most glaring aspect and the trouble in the path of integration, is the axis convention. As a convention, the body axis originates at the aircraft center of gravity. The positive X is towards the front, the positive Y towards the right wingtip, and the Z to the bottom of the aircraft. If this was a Russian aircraft, the Y and the Z axis are interchanged. So will be all other axis reference systems. Any trained person will find this change in axis system very inconvenient, especially if a person is involved in a program and he has to work interchangeably between two axis systems. It's a nightmare. These inaccuracies led to various problems such as pointing errors, improper work control, and other possible phenomena during flight testing. The next noticeable challenge was a difference in the manner certain parameters were handled by the Russians when they were at the extreme conditions. When integrating an equipment which took these questionable parameters for the algorithm, computations, and decision making, things had grossly gone wrong. For example, a flight test program which was basically conducted to assess the performance of an European equipment on different platforms, which incidentally included the legacy Russian platform. During flight tests, unexpected warnings of air-to-air collision would be heard. This was really confusing. To make the matters worse, this was in a networked environment. The entire team was on a wild goose chase, trying to find the errors in the network rather than raising suspicion on a particular platform. After in-depth analysis, this was attributed to a speed criterion. To give you a little more detail, on the legacy Russian platform, a speed below 200 kmph was considered invalid. So the system did not perform any validity check for the particular parameter. However, when the same parameter was being used by the European counterpart, things went wrong. Once this problem was identified and fixed, all the problem vanished. The errors in the speed channel was not known until the problem emerged during flight testing. The next issue was the usage of different standards for data transfer. For example, the Aero 429, For example, the Aero 429 transmits at 12.5 as well as 100 kbps. This is known. If the Aero 429 was there on a Russian platform, it would transmit at 12.5, 100, which is okay. Data rates of 50 kbps was not known until the beginning of integration. To complicate the matter even worse, different LRUs transmitted at different rates within the same platform. Limited visibility into these rates led to large integration problems. I think slides have changed a little. I'll just go back to the previous slide. Similarly is the issue with the video scanning. The normal practice is to use a horizontal scanning, which we see in a day-to-day television. The Russians use a vertical format. Now you can imagine the trouble if we are trying to use a single display to display both the Russians and the Western video. This part we have already covered. We'll come to the next one. One of the most interesting aspects and the point to note is that Russian LRUs were custom built to fit in the aircraft. This is a very good point as it saves a lot of space. But imagine the LRU is going to be replaced, and it's going to be replaced across different platforms to maintain uniformity of inventory and some idea of that sort. The problem becomes manifolds. We couldn't find an LRU which was exact mechanical match, and this was a major issue. One case to amplify the previous problem was a case of stabilization of the ground target, which we faced in one of the programs. Can we have the audio, please? As you can see, the pilot is in an attack. Keep a careful look at the stabilized marker.
Going up, God knows. Not all.
The CCR point would never stabilize, irrespective of whatever fixes were done. This had put the entire program in a turmoil. After a lot of struggle, it was attributed to a minor irritant, that is, mounting of the sensor on the platform. As brought out previously, certain modifications were done for fitment of this sensor on the platform. The minor modification resulted in major problems. A good lesson to be learnt. The simplest assumption in flight testing can cause the biggest problem. Once the problem was identified, software fixes were carried out. You can see the problem of stabilization of ground target does not exist. This problem was a history to talk about. These were few of the challenges that we faced due to ideological differences. There was a complete different set of problems we faced when we came to the electrical side. For example, during the flight testing of a legacy Russian platform fitted with a Western navigation kit, the system would align for approximately 3 minutes. The pilot would power up the engine, and just before he's ready to taxi out, the entire system would dump or recycle itself. This was a cause of concern, as the operational role of the aircraft was being compromised. With all protections in place, the same problem would reoccur. Cause of the problem? Uncontrolled spikes in the video. Uncontrolled spikes in the electrical power supply. These uncontrolled spikes, to tell you gentlemen, is only seen on the Russian platform. The designers had to implement radical solutions to overcome this problem. Another problem related to electrical characteristics were the cases of premature failure of LRUs when they were connected in series or along the circuit with the Russian equipment. Reason? The safety mechanism of the Russian equipment was so robust that they would short circuit the input and resulting in large currents being drawn from the Western equipment and ultimately the failure. Special circuits had to be designed to overcome this particular issue. Coming to another interesting aspect, that is the weapon integration. The weapon integration posed two distinct problems. One, integration of the Russian weapon on a platform with Western avionics, and two, integration of the Western weapon on a Russian platform. Oops, I'm sorry, I can see this slide going all over. Western weapon generally came with a rating of a variation of 4 to 5%, whereas the Russian weapon, the variation was around 12 to 15%. The whole question pivoted on how to deliver a Russian weapon with a reasonable accuracy. The solution was by making the weapon delivery algorithm less sensitive to the parameter which varied the most, in this case, the mass. Now the flight test program became even more complicated because it had to involve weighing of individual bombs, calculate theoretically the effect of change in mass, validate these results, and further revalidate the entire algorithm once they have been made insensitive to mass. Not an easy task. The next issue was with the mechanical integration. Weapons of the Western origin would not fit on the Russian platform and vice versa. This was because the Russian aircraft used a suspension lug which was 10-inch apart, whereas the Western counterparts used a suspension lug which was 14-inch apart. There was no way you could fit a 14-inch and a 10-inch and a vice versa. It was a problem. The seemingly impossible problem had the simplest of the solution. That is, to weld an additional pair of lugs to the diametrically opposite to the existing pair. So it caters for both the platform. Simple but a very effective solution. When all the issues of mechanical integration and weapon dispersion were sorted out, the next challenge was a large number of unknown parameters or behavior due to the limited visibility. Parameters such as rack delay, behavior of the weapon control system, and armament reference lines had to be found out by carrying out experiments on ground on the aircraft prior to flight testing. These parameters were unique to the Russian platform. As brought out by my friend earlier, the philosophy of the Russians was to use dumb weapons as a large area weapon. Hence, the sense of these parameters as calculated by this platform was biased towards this philosophy. The philosophical differences had to be solved by software compensation. Here is a video of a dumb bomb being dropped from a legacy Russian platform, upgraded with Western avionics. The bomb is being delivered from high altitude. The point to note is that this is a dumb bomb and not a guided weapon. The results are for everyone to see. The end product is a platform capable of delivering a dumb bomb with a reasonably good precision. We are able to combine the best of the West and the East. One surprising aspect emerged during the gunfire. The vibration levels shook the team awake to a reality called the gunfire vibration. The video is the HUD of a legacy Russian platform. The pilot puts the aircraft in a dive for a gun pass. Can you have the audio, please? The point to note is this video is taken after all the fixes have been carried out. Okay, as you can see, there was a large level of vibration. It was surprising to see how the Russian LRU performed under such high levels of vibration. To make a Western LRU function under such instances, additional care had to be taken during installation. Not all was bad. When solving these problems, there were a lot to learn from the Russian philosophy. One example is the case where a 8-bit system was used to get a resolution of a 10-bit system. The system attained this by using a sawtooth logic where the entire range was split into 4 steps, with each step having 256 levels, and hence 8 equals to 10 as per the Russians. During the entire course of flight testing, the Russian platform showed remarkable resilience to any sort of electromagnetic interference. The system did not have any effect as a source or as a victim, not often seen on the Russian platform. The list of challenges and the lessons learned are endless. These are the few engineering challenges that we faced during the course of integration. Now, I hand over you back to Sinha to cover a few aspects related to flying.
Thank you, Anwar. Well, gentlemen, till now we have seen the technical incompatibility of Western systems with the Russian platforms. Since these integrations often involved structural modifications or change in external configurations, the effect on handling qualities also required attention. But here we have some good news. So finally, we have something that re-emphasizes our faith that our books may be different, but our brains and hands work the same way. To elaborate, when a production Russian platform is evaluated against MIL standards on flying qualities or on Cooper-Harper scale, it would invariably score level 1. During systems and weapons integration, as long as the weight and CG changes were minimal, there were insignificant changes in handling qualities. The minor deficiencies in handling qualities were compensated by the improvement in display system. We have also realized that with advancement of display systems and increase in accuracy and reliability of the sensors, user-cued environment can be effectively used to compensate for minor handling qualities issues. While the handling qualities does not pose any major challenge on legacy platforms, such integrations on modern control-rich platforms such as the Su-30 may not be that easy. The primary reason is the flight envelope of this aircraft, which involves no limit on angle of attack or minimum airspeed. Thrust vectoring provides an equivalent aerodynamic surface which is largely independent of angle of attack or airspeed. It also nullifies the conventional relationship of aerodynamics and stability. Just to emphasize on this, I have some flight data here. Now here you can see the airspeed, which is 440 kilometers per hour, roughly 200 knots. And Y, if you recollect in our convention, this is NZ or the load factor. Pitch rate at this stage of about 25 degrees per second, and an angle of attack of 31 degrees. As I continue to reduce the airspeed, initially the angle of attack would increase and the same load factor and pitch rate would be maintained. This is pretty conventional. There is nothing wrong with this. But thereafter, if I continue to reduce the airspeed further, at the same angle of attack, still the load factor and the pitch rate will be maintained. Now at this stage, the airspeed is roughly 15 knots, load factor of 2, and a pitch rate of 11 degrees per second. This is definitely not conventional. And it is difficult to simulate these conditions and these conditions on ground. And therefore, any structural modification and its effect in these kind of flight regimes, the prediction for this becomes very difficult. This results in challenges involved during flight testing. Comparatively, the podded systems are much easier to integrate because invariably they involve restrictions on flight envelope, and the platform usually offers wide range of CG variations. Now coming to the human-machine interface. Human-machine interface for systems integration once again poses many challenges. The problem involves switch position to orientation of the display in case of certain systems. In case of the MiG-27, the whole cockpit was redesigned, which was part of the program. This is the original cockpit, and this is the redesigned cockpit. This redesigned cockpit was based on the operational employment philosophy at micro level, which operated on the platform on an integrated avionics environment and required HOTAS and good cockpit visibility. The redesigned cockpit found a great deal of appreciation from the users at field level. Gentlemen, while integration of Western systems on the Russian platforms poses many challenges, the enhancement in capability far outweighs the difficulties encountered. As a result, the IAF fleet today has gained sufficient capability enhancement at a much lower cost. We hope that the presentation has provided you all with some insight into the basic issues involved in such integrations and brought us all closer on this forum of global cooperation. That brings us to the end of our presentation. If there are any questions, we would like to answer them.
Number 37 degrees angle of attack, 35 degrees angle of attack on MiG-27, that is the order you go?
That's of a modern platform.
Thank you, Wing Commander Shakir and Wing Commander Sinha, for your talk on integration on Western systems and weapon on Russian fighter aircraft. I think the presentation adequately highlighted the power of innovation to empower the force, as it were, in this particular case, the Indian Air Force. And this can be only brought about, as we have seen in this particular session, also in the previous presentation, through effective test flying and engineering. The Indian Air Force has a number of legacy systems in the form of Russian aircraft, large fleet, as well as relatively modern Western-oriented aircraft, as also coming category of Su-30 MKI class of Russian aircraft. And this kind of cross-utilization of what we understand of the systems is extremely important to be able to extract that extra bit of mileage that would give us a little bit of an edge in making the force that much more relevant and potent. So thank you very much.